Okay, so we're on using the standard reduction potential table, abbreviated SRP table, to predict redox reactions. And I'm skipping the warm-up, so we're going to go straight to using the standard reduction potential table here. Okay. In my book, the table is on page 507 in the back, like the complete table. It's probably on a different page number in your book, but you may want to flip to the back and earmark the page because we're going to be using it a lot.
So just go to SRP.
Go to table A7, I believe. Standard reduction potentials of half cells. You good? Found it? Is it the very last page? Okay, and it's really small. Yeah, so we're going to be using that today to predict what species is actually going to give electrons or take electrons. Did everybody find it? Everybody has it? Okay. And the oxidizing agents, you will notice, are on the left-hand side of the table. Okay, and I'm going to bring the table up here in a second. And then the reducing agents are on the right-hand side of the table. So what's going to happen is the reducing agents on the right side will only give electrons to the oxidizing agents on the left side if they're above them. So, in other words, if I'm looking at bromine in comparison to the chloride ion or silver, silver would give electrons to bromine because it's the reducing agent on the right, gives electrons to the oxidizing agent on the left that's above it. Does that make sense? So chloride cannot give electrons to bromine because it's above it on the right. So only lower right gives things to the left that are above it. So it's kind of like this clockwise direction of giving electrons. Does that make sense? Okay. Let's take a look at the next page here. So I've kind of already described this. So let's just go straight to, I'm going to skip this stuff and go straight to a practice problem because it really doesn't make sense until I show you how to use the table. So we're on this first practice set. And a lot of the questions that I've been getting about this section are, well, how do I know what species is giving electrons to something else? And it strictly has to do with its location on that table, okay? So let me bring up, let me find the table here. I downloaded it. I downloaded it, but I have to find it. Okay, let's bring this over here. Okay, I'm gonna try and make this bigger so you can see it better. It's kind of frozen. Give it a second. There we go. Okay. So we're looking for I negative and BR2, and I'm going to have you mark these on the table. So I negative is right here. Okay, everybody found it? Okay, and then your BR2 is right here. Okay. So the question is, will this spontaneous redox reaction occur? If so, they want the balanced equation. So it will spontaneously occur if one of the substances that you're looking at is on the right-hand side and below the other one on the left-hand side. Okay, so the electrons are going to spontaneously be given in a clockwise direction from I negative to BR2. Does this make sense? Okay, so since this is going to happen, we would write yes for number 1, and that's because I negative is below BR2 and to the right. Do you want me to write that down? Okay. So if we're going to write out the spontaneous reaction that's going to occur, you're going to have to write the half reactions and then make sure that your electrons are balanced. Now, since I negative is giving the electrons to BR2, you have to reverse the order of that half reaction there. So when we do this, we're going to write it as 2I negative going to I2 plus 2 electrons, and then you're going to leave the order of this half reaction the way that it is because it is accepting the electrons. The electrons are on the reactant side. So it's BR2 going to, BR2 plus 2 electrons going to 2Br negative 1. And then if you add these two half reactions together, we have the same number of electrons on the reactant and the product side, agreed? So these are going to cancel. And then what you're left with is the overall reaction. Doable? Yeah.
Yeah, why'd you change the iron?
I changed the order because the electrons flow from the reducing agent to the oxidizing agent. So in this case, do you see how the electrons are on the reactant side, but don't they need to be coming out? Does that make sense? So that's why I reversed the order. Okay, do you want me to do, what?
You always do that?
Yes. Do you want me to do one more? Number 2, you're comparing F2 and Al plus 3. Okay, so we need to find those on the table. So F2 is up at the very top. Let me bring this down so you can see a little bit better. F2 is the very first one at the top. And then your Al plus 3 is, I may have to make it a little bit smaller. Your Al plus 3 is all the way down. Let me make this a little bit smaller so you can see it. So there's your F2, and then your Al plus 3. Is it even on there yet? It's even further down. It's right there. Your Al plus 3 is all the way down here. Okay, so they're both on the same side. So I don't have an oxidizing agent and a reducing agent. I have 2 oxidizing agents. So this is not going to spontaneously occur. So this is a no. They're both oxidizing agents. Make sense? Sort of. Do you want to try number 3 and 4? Okay, so you guys got yes. So your SN is below and to the right of Ag plus. So therefore your electrons are going to flow from SN to Ag plus. And you had to reverse the order of this half reaction here for the tin. And there were 2 electrons leaving the tin, which means there have got to be 2 electrons going to silver. But since the half reaction for silver only has 1 electron, you'd have to multiply this half reaction by 2. Okay? And then that's going to end up giving you 2 silvers, 2 electrons, 2 silver ions, 2 electrons, and then 2 silver metals. And then the electrons will end up canceling. Got my 2 here, and then you have 2 here. And that's your overall reaction. Question?
So are you reversing it so that like that your 2 ones that they gave you guys are lined up? Is that just how you reverse it? Or?
So, all right, so this side has the reducing agent, right? And this side has the oxidizing agent. And since your electrons always flow from the reducing agent to the oxidizing agent above it on the left, you would have to write the half reaction for the reducing agent in the opposite direction. Okay? And then multiply by a whole number if the number of electrons don't match. We got that? Did you get to 4 yet? I'll give you a second.
I would get like 1/2 I2.
No matter what, it's still
Okay, I found I2 down here and CL up here. So the CL either has to be below and to the right, or the I2 has to be above and to the left, right? So this is not going to happen. This is a no. The I2 isn't strong enough of an oxidizing agent. Okay. All right, so could you do that on a quiz next time? So I'd always give you the SRP table. We can all use that. Okay. All right, let me go on to predicting single replacement reactions, and that's what we're going to end on today. Okay? Okay, so I'm going to make this table a little bit smaller because we're going to make some notes on it. Super small. And you know that metals and nonmetals are more stable as ions because metals give up their extra valence electrons to reveal the octet that they have underneath. And then nonmetals accept 1, 2, 3 electrons. There we go. It's not coming to focus. Let's see. Nonmetals are going to accept 1, 2, or 3 electrons to complete their octet. Can I fit all of this onto one? Maybe. I'll bring it back in a second. The video camera is not in focus, so I'm trying to let it sort of like fix itself, but it's not. It's just completely blurry. Work with me. Let's see if I can get it to. I don't think it liked the bright light. There we go. That was weird. Okay. Okay, so nonmetals have really high electron affinities because they need only 1, 2, or 3 electrons to complete their outermost shell. And you'll notice that the nonmetals are found in the upper left of the SRP table. So what I want to do is I want to make some notes here for you on this table, okay? All right, so nonmetals are strong oxidizing agents. So they're found here in this upper left-hand region of the SRP table. And you'll notice that the metals tend to be in the lower right region of the SRP table because metals are strong reducing agents. They like to give their electrons to nonmetals. So down here in the lower right region, I want you to write that metals are strong reducing agents. Most of them are strong reducing agents. And found down here in this lower right-hand region. Okay. So what we're going to take a look at are some single replacement reactions that are a type of a redox reaction. And we're going to see if a non-metal replacement reaction will happen or whether a metal replacement reaction will happen, depending, because there are two different types. And if you take a look at the next practice set on the next page here, where we're determining the outcome of a single replacement reaction. Remember, a single replacement reaction is either going to have a non-metal by itself with a compound, or it'll have a metal by itself with a compound. So if this is a non-metal here that's by itself, then it would possibly trade places with the non-metal that's in the compound. So we would call this a non-metal replacement process, okay? Whereas number 2 has got aluminum metal by itself. And you want to see if the aluminum is going to replace the copper in the compound. So this would be called a metal replacement reaction. So do you guys remember these single replacement reactions from the fall? Okay. So I just want to go through and label them as being non-metal or metal replacement, just so you know what you're looking for. Here, chlorine is a non-metal. This is a typo, by the way, on NaCl. Cross out the Cl and make it Br. And then this would be a non-metal replacement. And then for number 4, you've got tin by itself. You want to see if it will replace aluminum, so this would be a metal replacement.
For number 3, how come you're replacing Br instead of Na?
Because chlorine's a non-metal.
So it's just whichever one.
Yeah.
Okay.
Yeah. Okay, so what we're going to do is, something that confused some of my students last week was that when you're looking at the substance that's in the compound, these are all ionic compounds. So you're really comparing iodine, not with pure fluorine like F2, you're really comparing this with F-1, because that's the ion that's in that ionic compound. Does that make sense? And then down here, this is the copper +2 ion. You're not comparing it with just pure copper solid metal, okay? Here in this compound, you're comparing chlorine with the bromide ion, because that's the one that's in the compound. And then for aluminum nitrite, you're comparing it with the aluminum ion that's in the compound, okay? So we're going to do the exact same thing we did before. We're just looking at different substances in the SRP table. So go back to your SRP table. And let's take a look at, make this a little bit bigger. Let's take a look at iodine and F-1. So you've got iodine right down here. And then you've got F-1 up here. Don't the electrons flow from down here on the bottom right up to the left-hand side? So would you predict that this would happen? No. So this is a no for number 1. Because I2 is not strong enough. It would have to be above F-1. So I2 isn't a strong enough oxidizing agent. Okay. And then let's take a look at number 2. For number 2, we're looking for the Cu+2 ion and the aluminum. So let's bring this down. Your aluminum is here, and your Cu+2 is here. So would you predict that this would happen or not? Yes. So your electrons will flow from the aluminum to the Cu+2. But so this is a single replacement reaction, we have to write the full out reaction, and they want it in net ionic form. So you've got solid aluminum combining with copper 2 sulfate, which is in solution, and then you're going to form copper. Get rid of this. They're going to form copper metal and then aluminum sulfate. It's not balanced, so you would need to put a 2 in front of aluminum, and then a 3 here, a 3 here, and now it's balanced. When you're writing a net ionic equation, remember we only break down substances that are dissolved in water. So I'm only going to touch this substance and this substance. Okay. So there's everything broken down. And then we need to cancel out whatever spectator ions are present. That means we're looking for ions that are identical on the left and the right side. You've got 3 sulfate ions on both sides, so you want to cancel those. And then what you're left with is your net ionic equation. I'm not going to rewrite it because I don't have a lot of room. Okay? All right, based upon what I just taught you, why don't you take a look at number 3 and number 4 with the person sitting next to you, and let's see what you come up with. Oh yeah, yeah, yeah.
Is it BR? Oh, you could tell from okay, so BR2. Yeah. So BR2. Oh, no, sorry.
Did you get that? For that one.
Oh, wait, does that place go for that?
Yeah, it's 2 in front of NABR and 2 in front of NaCl.
Okay. So you have Cl2 dash plus 2 Na plus 1 AQ plus 2 BR2 AQ 2 like BR2 liquid plus 2 Na AQ plus 2 Cl AQ.
But make sure the charges of the
Okay, can I explain 3? So for number 3, you had your bromine further down, right, than chlorine. So you were going to be giving electrons from bromine to chlorine. So we completed the single replacement reaction. You should have gotten this. If you look for the states of matter on the SRP table, they gave them to you as gas and liquid, and that meant that these salts were just dissolved in water. And then you're breaking down this and this because you never touch solids, liquids, and gases when you're writing net ionic equations. So you have 2 sodium ions, 2 bromide ions, then again you have 2 sodium, 2 chloride on the right hand side. And then you need to cancel out whatever your, I'll put a +1 there, whatever your spectator ions are. So those would be the ions that are the same on the left and the right hand side, and then this is what you're left with. Yeah? Okay, did you get to number 4 yet? No? Okay, I'll give you a second for that one.
I did review questions, so it's like sense, but I usually go up like 5 times a day. Go up the foot. Yeah, I was what do you do? I just don't know how to do it. Okay. What's it easier like sign it first and then that goes already on the calculator, but like I forget how to do like the
Okay, what'd you get for 4?
like
No, yeah, it's a no because your Al plus 3 is here on the left hand side on the bottom, and then your tin metal is over here on the right hand side above it. So this tin cannot give electrons to aluminum because it's to the left and below it. So it's not, this aluminum ion is not a strong enough oxidizing agent. Okay, understand? Questions for me?
So the quiz is going to be like